Today we are going to talk about the temperature dependence of rate constant. Talking about the dependency of the temperature of the rate constant. So based on this, the dependency, so you can plot the log k versus 1 over t. The reason is the rate constant can be equals to k0 times exponential minus activation energy divided by kt or RT, depending on the unit of the activation energy. So when we want to investigate the temperature dependency of a rate constant, you can have a log on both sides and plot the log k versus 1 over t. And the intercept will be log k0. And also the slope will be minus activation energy divided by R here. So how to plot or how to draw this or get this relationship between K and as a function of temperature. So for example, I can choose at T1, then T1, when you measure the consumption rate of reactant, can express like a K1, Ca to A, Cb to B. In order to investigate the temperature dependency, don't forget you need to maintain or remain the concentration of reactants remain constant. And the only parameter you change will be the temperature. Okay, so under this situation, you can write this down, right? As long as I formulate this result, I can measure the R1, right? Then I divided this term and this term, then I can get a K1. And log K1, I can plot the log K1 at 1 reciprocal of T1 probably will be this data at this data point. So at T2, I can measure R2, the consumption rate of reactant, and also K at equals to K2 times the concentration of reactants and to the reaction order. Okay, so as long as I use R2 to divide it by the concentration part, I can get the K2 and log K2, and the horizontal will be reciprocal of T2. Then I can draw this data point. So after fitting, I can get the temperature dependency of the rate constant. So this is the whole idea. And someone want to explain this slope, so they will use this divided by this and log this R2 divided by R1. So you will find due to the concentration of reactant A and B remain constant, so the consumption rate of reactants is proportional to the rate constant. Okay, because lists are the same, right? So this proportion with K2, okay, then you will get this result. Directly use this term to divide it by this term and take a log, and you can get this results. And actually, if you look this carefully, this actually is talking about log R2 minus log R1 is this distance, right? Okay, it's Y, and the 1 over T1 minus 1 over T2 actually is this one, right? So it's the slope, right? So it's Y equals to slope times X. So this slope is a minus activation energy divided by R. Okay, so it's the same idea. Okay, so following in your textbook, they highlight some points, 3 points. So I'm going to explain this step by step. K with high activation energy is more temperature sensitive than that with lower activation energy. So the slope is corresponding to the activation energy. So if I have the higher energy, activation energy 1, and also have a lower energy, activation energy 1, I have 2 chemical reactions. And when I monitor this temperature regime, and based on the sensitive actually means which one has a higher slope, right? So the slope here for the higher activation energy 1 have a higher slope compared to that in the in the reaction with the lower activation energy one. So the higher activation energy one is more temperature sensitive, which means when you increase the temperature, then this one you can increase the rate constant significantly. Then this means we have a temperature sensitive rate constant. And the second point actually is highlight that the rate constant at lower temperature regime is more temperature sensitive than that at high temperature. What this means temperature sensitive, so the indicator they point out is at low temperature regime, when I increase by 100 K, I can almost double the log K. But at higher temperature regime, I need to increase the temperature by 1000 K, which is 10 times larger than that in the low temperature regime. Then I can also double the log K. So this is why they say at a lower temperature regime is more temperature sensitive. The K is more temperature sensitive. It's easy to double your K, the log K. And based on these results, we also know that the activation energy, the slope, means the activation energy can help us to determine the reaction mechanism. What this means if when you try to plot log K versus 1 over T and you observe this, after fitting you find it's a straight line, which means that there's only one chemical reaction involved in your reactions. But however, if not a straight, probably it would be a curved line, like this way or this way. So for sure that tell you that there are multiple chemical reactions involved. So I'm going to explain this case, but first of all, you need to know, as long as you plot the log K, you measure the K at different temperature, that will help you to determine how many chemical reactions involved in your experiments during your interesting temperature regime. So for this one, because I got a curved line, right? And at lower temperature regime, this is lower temperature regime and this is higher temperature regime. And as you expected, I will fit this curve with straight line. Then I can get the red line with E1 activation energy and also have the other straight line with E2 activation energy. And based on the slope, I know E1 is much larger than E2 because I have a higher slope. Okay? And next, I'm going to take a look carefully here. I find that at higher temperature region, this region, our experimental data means the K I measure in our experiments is more close with the reaction 1 with E1, right? With activation energy E1. And when I decrease the reaction temperature to low temperature regime, I observe the K I measure from our experiments is more close to the reaction with E2 activation energy. So based on this, what did I find here? At higher temperature, at high temperature, I find at this temperature, specific temperature, I find E1, this chemical reaction with E1 activation energy is dominate these experiments, dominate compared to the E2. Why? Because the K major in our experiments is more close with that in the chemical reaction with E1 activation energy. And the same idea, when I take a look on And also this one has this E1 actually has higher rate constant compared to this one, right? This will be lower with a lower rate constant because the log K is smaller than this one. So at high temperature, the fast one dominates. And at a low temperature region, I find that the experimental data is more close to the reaction 2 with activation energy E2, right? And regarding to reaction 1, I can say reaction 1, the K is quite small, right? So this is also the faster one for the reaction 2. So based on this result, we find faster one, this is faster than this, right? And this also faster than this. So what's the relationship between the reaction 1 and reaction 2? Always faster dominate. So based on the always faster reaction dominate, so the reaction would be the parallel reaction. Because if they are parallel reaction, then for parallel reaction, for example, like A will transfer or generate R. So faster one dominate, always the faster one dominate the reaction, right? Dominate reaction time. How fast to dominate, how fast or how slow it is. And the other case, if the curve after measure the log K at different temperature, then you got this kind of curve. And also low temperature region, high temperature region. And based on after fitting, you fit it with reaction 2 and reaction 1. And here, reaction 1 has a higher activation energy than reaction 2. Okay? And this is our experimental observation. So at high temperature, we can see that the K actually is more close with the reaction 2. And reaction 2 compared to the K in reaction 2 actually is slower than that in reaction 1. And at low temperature, also the K is more close with reaction 1. And reaction 1 also is a slower one compared to reaction 2 at this specific temperature. So in this case, slow is the one always dominate the slowest one dominate the total overall reaction rate. So slowest dominate, so that means the relationship between the reaction 1 and 2 probably will be the series reaction. So let me explain why it makes sense. Because what's a series reaction? A will generate X and X will generate R. In order to get the generation rate for R, A need to convert it to X, right? So if it spends lots of time to convert it to X, then this time will dominate the whole the reaction rate of whole reactions to generate product R. Okay, so for series reaction, always slowest one will control or dominate the reaction rate for whole reactions. And for a parallel one, A directly generate R, so the fast one usually will dominate the reaction rate here. Slow for series reactions, slow path dominate. Okay. So I'm going to give you a summary here. So the rate equation will include the temperature dependency or also the concentration dependence. Okay. So in order to know the activation energy part, you need to keep the concentration of reactants constants, then you can know, and you plot the log K versus 1 over T, then you can get the activation energy or energy barrier for your interesting chemical reactions. But if you are interested in the concentration reaction orders, then you need to perform your experiments at constant temperature and measure the concentration of reactants as a function of time. then you can have a chance to know what's the reaction order here. And this is we talk about inhomogeneous chemical reactions. But if the one we deal with would be heterogeneous chemical reactions, so you need to consider the mass or heat transport between different phases. And if the one we deal with is non-elementary reactions, because it is non-elementary reactions, so you need to reconstruct its kinetics model, which means you need to find out this non-elementary reaction is composed by which two or three elementary reactions. Usually in our cases, usually you can just make a two elementary, you can make an assumption to assume they are two-step process. And when you try to plot log K versus 1 over T, this type of analyze method will help you to determine the activation energy and also show you which mechanism is a rate limited step. For example, like the slowest one, this is the rate limited step. Okay? So let's move to the second part, how to analyze your reaction data from your experiments to get the reaction rate equation for your interesting chemical reactions. So the purpose here is to get the rate constant and also the reaction order. So what to analyze can simply classify into concentration dependency and the temperature dependency. So to get the concentration dependency, the one you need to do is you need to keep the working temperature constant, and you measure the concentration of reactants or products as a function of time. So in this case, you can get the concentration dependency. And regarding to the temperature dependency part, this part actually you need to keep the concentration of reactants constant, then you measure the rate constant here, or the consumption rate of reactants or products at different temperature. Then in this case, you have chance to know the temperature dependency. So here we are going to introduce you two methods to analyze your reaction data to get the rate constant and also the corresponding reaction order. So the first method we call the differential method. So, and the second one is we call the integral method. For the differential method is you can find the consumption rate of reactants per volume from the kinetic data before attempting the fitting precision. So from the kinetic data means you can measure the concentration of reactants as a function of time. This is we call the kinetic data. And the change rate of the reactant or consumption rate of reactants will be, as long as you have a concentration versus as a function of time, and to get this consumption rate will be the slope for each data point, right? So in this case, it is good for complicated rate equation forms, but need reliable data. Means you need to measure the concentration of reactants or products accurately. So means reliable data. Otherwise, the slope, as you know, we consider the slope, right? As long as there's a variation in your data point, then that will result in a bigger variation in the slope. So finally, you will get you cannot get a correct or accurate reaction order. And regarding to the integral method, the one actually is different. You need to, first of all, you need to guess is this reaction belong to zero order, first order, or second order? Because for each different reaction order, we have a particular form of rate equation. So the only thing is, as long as you get the particular form of rate equation, you can just input all the data point you collect or recorded from your experiments, then to see whether it fits to that specific rate equation. So this is easy to use because you already have specific form of the rate equation for specific reaction order. But so it's easy to use, right? You just input all the data points here to see whether it fitted. But it can only be applied to specific rate equation form. For example, you only have 3 particular form of rate equation. It's zero order, first order, and second order. So you cannot deal with like the reaction order is like for example is 1.2 or 1.5. You cannot deal with that. Okay. So let's talk more about these 2 methods. The first one we want to address will be the differential method. And under this part, actually, your textbook show you if you have no idea about the reaction order, the author will suggest you to use the differential method, okay, to analyze to get the reaction order. So I'm going to give you an example how we perform the differential method to get the reaction order. So what we have here is we have a chemical equation is a chlorobutane react or dissolve in the water, then you will get the butyl alcohol plus the HCl. So regarding to the, I want to correct this one. So it will be the irreversible process will be better. And in this case, how to perform the differential method to get a reaction order for this chemical equation. So we just correct or recorded the concentration of the chlorobutane as a function of time. Just recorded that, then you can see the concentration decrease as a function of time, and you got lots of data point, right? So then we try to plot the concentration of Ca, which is the chlorobutane, as a function of time. Then we draw this smooth curve to represent the data. And then don't forget what's the rate equation for this consumption rate or rate equation. For this equation, you can express like the minus Ra is consumption of reactant A equals to minus dCA over dt, and also equals to Kca to N. N is a reaction order, is the one we want to know. So based on this dCA over dt, actually you have the Ca versus the T, right? So this results actually, you can just take the tangent on each data point, so you can get the slope for each data point, then you can get the consumption rate of reactants, right? So based on this idea, you can get several consumption rate of reactant A at different time points, okay? So this is the minus Ra consumption of reactant A. So, but I for sure I have different slope, right? So which one is the correct one to help me to get the reaction order N? So next step is, as I mentioned, I need to determine the slope, right? So next, because you can get different slope for each data point, so how to based on this information, how can I get the N? So the idea will be that you take a log on both sides. So for example, like can get the we draw something? Okay, so you can take a log on both sides. So you will get the log minus RA versus log CA. So if you take a log on both sides, you will get log minus RA equals to log K plus N log CA. Okay, so based on these results, so as long as I use this as a y-axis, y, and this as a x, and I got several data points, right? So the slope would be the reaction order. So this is the whole idea. Okay, so let's move forward. So from the log minus RA versus log CA, then you can get the slope and also the intercept to get the rate constant here. So based on this idea, starting from this data point, so log CA concentration, log CA, here CA I input 0.09, and the slope I can get probably I get the minus RA and I take a log on it. So I'll get this data point and also this, and this. So I get several, for example, I get several data points from here to 0.02. I just randomly pick up 4 data points. Then the slope actually is equals to the reaction order. So after fitting, I can get the reaction order N. If you have more data points, that will help you to get the more correct reaction order for these chemical equations. But as you know, there's a very big disadvantage or drawbacks for using this differential method, right? Because if you cannot get a very correct data point, then after take a slope on each data point, then the variation will be quite large. So after fitting, even after fitting, you still cannot have a correct reaction order. So in order to overcome this kind of difficulties, as you know, when we perform the experiments, always there are some errors, experimental errors come out, right? So in order to minimize these errors or deviations, so your textbook suggests you, instead of take the slope for it, take the slope to get the consumption rate for specific time point. Why don't you try to use the half-life time analysis? So half-life time analysis, actually, the idea is similar with a previous one, but we don't take the slope for each data at a specific time point. Instead of that, we consider the half-life time, which means when concentration of reactants drop to 1/2 of its original concentration, then how much time it takes. We call it as a half-life time analysis. So the same idea, when I have the methyl isonitride and will convert or generate to acetone nitrile, in this case, I also measure the concentration of reactants as a function of time and draw like this to get this curve. And instead of get the slope for each time point, at this moment, I try to measure or analyze how much time it takes to allow the concentration drop from 115 drop to half, so it will be 75 total, right? So this is a half-life time. And if we consider 75 in the beginning, and when it dropped to 1/2 will becomes to here, so it's also, this is a half-life time. We just focus on the half-life time. So this method, we just recorded the half-life time. And also the corresponding C0 for this case will be 115, and for this case C0 will be the 75. I just so why and how we can use this half-life time to help us to get a reaction order. So I'm going to explain this in this slide. So this is we also call a fractional or half-life time analysis. And we have a chemical equation show like this: alpha A react with beta B, and you can generate probably, and this you have C, D, E, and so on, and you can generate products. When I try to write down the rate equation by using the consumption of reactant A expressed like minus dCA over dt, will be change rate of reactant A, and equals to KCA to A, CB to B, and so on. So based on this, we know the reactants with stoichiometry ratio means the alpha A for sure would be reacted with beta moles of B. So when you try to formulate a relationship between CB divided by CA, I will say beta equal to beta divided by alpha. So I try to rewrite this rate equation here and just try to substitute the CB as beta divided by alpha times CA, put here, to B. So next I'm going to organize them, arrange them, and put a CA together. So we have CA A to B, A plus B, and the rest of coefficient put together. Okay. So now I can rewrite this rate equation and express like this: minus dCA over dt is consumption rate of reactant A equals to this, can consider as a K, and use this symbol to represent it, this K times the beta alpha to B, and so on. And the most important part is what we are interested in is CA to A plus B. This we will summarize as a reaction order. No matter because actually probably this reaction also have C, D, E, F, G, no matter what type of it is, you also can summarize them into the reaction order N, right? So now we have these equations. So next I'm going to do the move to CA to N, move to left-handed side dt to right-handed side, and take the integral for both sides. And so let's try to okay. So you can like this, because you okay. So probably I can write here. So minus CA and you put the K dt here. So you take the integral from both sides, starting from when t equals to 0, the CA is CA0, right? And when time move to t, then CA equals to CA. Okay, so after you perform this integration, so you will get this equation. But during the derivation, this equation can be performed under when the reaction order not equals to 1. Okay, so under this situation, you got this equation right. So next, as I mentioned, half-life time means the concentration Ca dropped to 1/2 of Ca0. So you just put the 1/2 of Ca0 put here. So after arrangement, you will get this results. And just remind, because here I focus on the half-life time, so I highlight this one, one half, right? So you also can instead of monitor the half-life time, you also can choose like one third, or a quarter. Okay, so it doesn't matter. So in your textbook, they use F to represent the fraction. Okay, so now you have this relationship. So based on this, how can we get the reaction order n? Easy, right? You just take the log on both sides and plot the log t 1/2 versus log Ca0, and the slope will be, after fitting the slope, will be equals to 1 minus n. So this is the idea. As I mentioned, I draw the log t 1/2 versus log Ca0, and let's try to input the data. So based on the previous one, the concentration dropped from 30 to 15. How much time it takes, and I take a log on this time, and the horizontal axis will be a log 30, because Ca0 is log is 30, right? And the other data probably I monitor the time is spent from 30 drop to 20, so log time, and the horizontal axis is log 40. And the same idea, when I monitor the time is spent from 15 drop to 25, and log the time, and the horizontal axis will be log 15. Then after fitting, so I will say the slope will be 1 minus n. So based on this, I can get the reaction order n. Just a quick remark, in this case, the tricky part, or the one you need to pay attention part, is this reaction, or no, this relationship, or this relationship can only, or this analyze method can only be applied while your reaction order is not equals to 1. Okay, so I'm going to give you an example here, and to show you how can we use the half-life time to analyze the reaction order. So what we have here is we have the reactant A decomposed to generate product R, and I try to measure the concentration for reactant A as a function of time from 0 minutes to 80 minutes. So the same idea, I try to plot the concentration of reactant A as a function of time, and use the smooth curve to represent this data point. And this is the equation I derive. So before I use this half-life time method, I need to make sure this reaction is not belongs to first order reaction. As long as I confirm this, then I try to monitor the half-life time. So it was, the concentration Ca0 is 20, when it dropped to 10, so the time will be 18.97. And next point, data point, I will focus on the 15 molar, when the concentration dropped to 7.5, so the time will be 28.11. And the third one will be the concentration drop from 10 molar and drop to 5, so it will be, the time it takes like 43.2 minutes. So now I have this the half-life time, right? And also I have the Ca0 for different data point. So next, I just want to plot the log half-life time versus log Ca0. So the data actually I have is log the time, half-life time, I got a 2.94, and this is a vertical 2.94, and the horizontal will be log 20, and this one is a log half-life time is around 3.07, and the horizontal will be log 15. and this one is 3.18, and the horizontal axis will be 10, log 10. So as long as I get these 3 data points after fitting, I can get the slope is minus 0.36. And based on this equation you learn, actually the reaction order will be equals to 1.36. Even though you got a reaction successfully to get the reaction order expressed like this, but don't forget, in order to reconstruct or recover the rate equation of your interesting chemical equations, you need to put this back and to get the K. Okay, so in most of cases, when you put the N equals to this value and input the half-life time and corresponding concentrations, then probably you also will get 3K. Then you take the average for this 3, then you can have K, the value for K. Then you can reconstruct the rate equation for your interesting chemical equation. Okay, so this is very important.